titled as Testing Flavors of the Early Universe Beyond Vanilla Models with Cosmological Observations. Today he is going to talk about the quantum mechanical origin of cosmic structures. So Vincent, the stage is yours.
Thank you very much for the nice introduction, and let me take the opportunity to thank IMSC for having me today. Thank you very much for coming, all of you, and thank you, Dheeraj, for hosting me today. So I'm going to talk about one of my favorite research topics, which has to do with the way that quantum fluctuations in the early universe gave rise to density fluctuations and to structure that we can later observe. And in particular, I'll be interested in seeing whether we can prove that the structure that we see in the universe come from quantum fluctuations. So I will start with I will try to start. Okay, with a brief introduction about cosmology and how we understand the way that structures form in the early universe. And after that, I will focus on the quantum mechanical mechanisms behind this scenario. So this is a sketch of the universe as we understand it today. Now we have observational evidence that the universe is expanding. And because the universe is expanding, when you go backwards in time, the universe is smaller, therefore it's denser and hotter. And so matter behaves in different ways. Okay, so nowadays, the universe looks like something you see on the right-hand side with galaxies, and inside galaxies, stars and planets and so on. But as you go backwards in time, those galaxies started to exist only at a given time. And there was even a time which is before this line here on the left corner, where the universe was so dense that it would not allow light to travel in a free way. So at this early time, the universe was opaque, and there is nothing we can directly observe, at least with photons, because light does not travel freely. And then at some point, the universe became transparent, and the light, which comes from this event, which we call the last scattering surface, because it's the last scattering event that photons underwent, is called the cosmic microwave background, which we have observed and measured to a very high accuracy, and that gives us information about what happened before this last scattering of the early photons. So what we know now is that what happened before this last scattering is mainly a phase of cosmic inflation. So I will just explain briefly what cosmic inflation is. So on the top of the screen here, you have an equation which describes the geometry of a universe that is expanding. So if you set this A parameter to 1, then you just recover the flat Minkowski spacetime metric. But now I allow my spatial hypersurfaces to have a size which depends on time, and it depends on time through this A of t function, which we call the scale factor. So as the universe expands, this A of t function increases as a function of time. And this describes the geometry. So in such a universe, you can construct, there is only one free function of time, right, A of t, so you can construct one dimensionful parameter, which we call the Hubble parameter, which is A dot over A, and which has the characteristic dimension of a time scale. 1 over h is a time scale or length scale if you set the speed of light to be 1, which characterizes the expansion. Now, if on top of this expanding background, you try to describe matter with fluids or fields, and if you expand those fields into Fourier components, then what you find is that the dynamics of each Fourier mode very much depends on whether the wavelength associated to that mode is smaller or larger than this characteristic length scale. Okay, so if the wavelength is much smaller, it means that it is smaller than the scale which describes the curvature of space-time. So you have a field on top of a curved space-time, but in fact, locally, you don't feel that you live on a curved space-time, okay? It's exactly the same as if you perform experiments in the lab. Even though you live on a flat surface, which is the Earth's surface, you don't need to take into account that you live on a flat surface. But if you carry out experiments between, I don't know, India and the United States, then of course you need to measure things along the curved surface. So in this regime, you don't feel that you live on an expanding background, so you're insensitive to space-time curvature, and this is very convenient because it gives rise to unambiguous vacuum states for your field. While on the right-hand side, you happen to live you happen to feel the effect of the curvature, and in this regime you have a quantum field on a curved background, and so whenever you have a quantum field on a curved background, you typically have quantum particle production. Okay, so situations in physics where this happens are common. One example is the Schwinger effect. If you apply a strong electric field to a cavity, you tend to create particles with opposite charge out of the vacuum, which go in different directions. So you create particles out of the vacuum. Another situation is the Hawking effect close to the horizon of a black hole, where the gravity field is so strong that it also can pull particles apart out of the vacuum. And so another situation is cosmology. If you have an expanding background in this regime, you will also have this particle production mechanism. So essentially, the expansion of the universe is so fast in this regime that particles can be created out of the vacuum and pulled apart before they have time to recombine. So you also create particles out of the vacuum. So in the early universe, there is this phase of inflation, which corresponds to a regime where A double dot is positive, which means that, so A dot positive means that the universe is expanding. A double dot is positive means that the speed at which it expands is itself increasing, okay? So there is an accelerated expansion phase, which happens very early on. And if there is this accelerated expansion phase, you can show that the Hubble radius, which is displayed here in pink as a function of time, is almost a constant. So this phase early on is called inflation. Hubble radius is almost a constant. And so if now you look at the wavelength of your Fourier mode, which grows as a function of time as an effect of the expansion, you find that you go through these two regimes I was describing before. So initially you start inside the Hubble radius, you don't feel the curvature of space-time. And then, so you can set initial conditions in the vacuum state of the theory, and then you cross out the Hubble radius, the mode becomes larger than the Hubble scale, you feel the effect of the curvature, and so you create particles out of the vacuum. So in this regime here, you create lots and lots of particles. It's a very efficient mechanism. I will, spend some time describing it during the talk, such that at the end of inflation, I have populated space with classical, what looks like classical fluctuations. And those classical fluctuations, they later give rise to galaxies and stars and planets and everything we see in the universe. Everything which deviates from homogeneity arises from those fluctuations. Here I've also shown what happens after inflation, which is a phase dominated by radiation, by pressureless matter, and then some dark energy, but mainly I will be focusing on this early phase during my presentation. At some point at the beginning of the matter phase is the last scattering surface, what I was mentioning before. So remember, this is the oldest picture we can take of the universe, and by looking at fluctuations on this last scattering, we can get some information about those quantum mechanical processes. So this is just a picture of the last scattering surface as it was recently imaged by the Planck collaboration. So what you see here is the temperature of the photons which are coming from this last scattering surface. The temperature is almost the same regardless of the direction that you observe. So it's 2.7 Kelvin. But if I remove this 2.7 Kelvin, which is the mean value of the temperature, then what is left over is a tiny fluctuation. It's very small. You see it's of the order of a few tenths or a few hundreds microKs. So the relative amplitude is 10 to the minus 5 compared to the mean value. We have tiny, tiny fluctuations in the temperature field, which are direct imprints of those quantum fluctuations in the early universe. So there is a big activity around using those measurements to try and constrain what happens during inflation. So the way that we describe, that we understand those fluctuations in the cosmic microwave background during inflation is that we usually describe, because those are small fluctuations, we can describe them using perturbative techniques. So we typically expand the fields that describe physics. So there are essentially two types of fields. There is the metric, which describes the geometry of space-time, and then there is matter. So in the simplest models of inflation, inflation is just driven by one scalar field, so matter will be just one scalar field, which is this phi quantity here. And then you can show that there is a single combination of the fluctuation in phi and the fluctuation in g mu nu, which does not depend on the choice of coordinates. So we describe gravity with general relativity. General relativity is a theory which is invariant under changes of coordinates. Therefore, any physical quantity should not depend on the choice of coordinates. And it happens that there is a single combination which is indeed invariant. and which I will call V in this talk. And this V is directly proportional to the fluctuation of the temperature that you could see in this map. So of course, I skip the technical details. I just give you the main ideas here. The idea is to derive a theory for this V quantity. So it's a field, it depends on space and time, and to describe this V as a quantum field. Okay, we start from the vacuum state. At the initial time, we start inside the Hubble radius, so we know how to set a vacuum state explicitly. And we propagate this field throughout inflation, and at the end of inflation, we compute expectation values that we compare with observations. Okay, so what you see at the bottom left of the screen is a comparison between the expectation value of this V field and measurements. So more precisely, what you see here is like a power spectrum of the temperature fluctuation. Of course, because we measure the temperature on a sphere, which is this last scattering surface, so in every direction I can measure the temperature of the photons coming towards me. Because it's a sphere, I cannot do a Fourier decomposition. I rather do a spherical harmonics decomposition, which is like Fourier but on a sphere. So this is like the equivalent of the Fourier mode, which we call the multipolar moment. And this is the amplitude of the signal. The red curve is the result of this calculation, so taking the expectation value of the V field, and the blue dots are data points. And you see that they match perfectly. On this figure, you have something like 2,500 data points, different values of L, and the red curve is fitted with only 6 parameters. So it's quite a powerful fit. It's the square, yeah, it's expectation value of V squared. Yes, yeah, it's a 2-point function, so like a power spectrum. On the right panel, you have the cross correlations between the temperature of the photons and the polarization, so the direction of the electric field. And you see that again, you get a very good agreement. And this is the cross correlation between the polarization and the polarization, and again, you get the same agreement. Okay, so this theory of inflation seems to be extremely good at explaining the temperature and polarization fluctuations that we observe on the cosmic microwave background. So this is the state of early universe cosmology in a nutshell. So it is, of course, on one side very satisfying, but on the other side, it's also quite non-trivial. So what I'm essentially telling you is that we understand the formation of structures by the gravitational amplification of quantum fluctuations. But that means that we trust quantum mechanics is a valid theory on cosmological scales, which is a regime in which quantum mechanics has never been tested. So one question is, of course, well, can we trust quantum mechanics at those scales where no experiment has ever been carried out? Another aspect which is a little bit more fundamental is that because my field is a combination of fluctuations of the matter and of the metric, when I quantize this field, I also quantize the fluctuations of the metric. And this is not trivial, okay? We don't know how to quantize the metric. If we knew how to quantize the metric, that would mean we have a theory of quantum gravity, which we do not at the moment. There are candidates, but there is no fully definite theory. And so you may think that maybe the fundamental theory of quantum gravity, if it exists, prevents you from quantizing the metric fluctuations. Maybe I cannot do that. So here I'm doing something non-trivial. There is also another question which arises in this context, which so the two last questions I will not discuss during the talk, but I just wanted to mention them because I think they are equally interesting. One has to do with the quantum measurement problem. So in quantum mechanics, whenever you have a quantum superposition of different states, usually what the Copenhagen interpretation states is that you perform an experiment, and when you perform a measurement, the wave function of the system collapses to one of the eigenstates of the operator that you measure. And after the measurement, the state of the system becomes what you have measured it to be. In the early universe, there is a similar situation. So the theory does not tell you that the temperature of the cosmic microwave background should be this and that at those different locations. It does not tell you that there should be a galaxy here and nothing there. It rather gives you a quantum superposition of many, many different configurations. And somehow we take this and we derive probability distributions, and we compare those probability distributions with the statistics of what we observe. But in the meantime, in principle, something must have made the wave function collapse. And of course, you cannot say that it is a measurement, or because no one was here in the early universe to perform any measurement, right? You cannot also say that you performed the measurement, because well, if you collapse the wave function when you perform the measurement, but you exist because the wave function collapsed at some point, so it's sort of a circular argument. So there is this so-called quantum measurement problem, which already exists in quantum mechanics, even in conventional situations, but which in cosmology is even more acute. So maybe there is something to dig into at this level as well. And finally, a fourth sort of topic which emerges from those considerations is that maybe we can use cosmology to test quantum mechanics. Okay, so I said we don't have any experiment which tests quantum mechanics at those scales. Well, we have at least cosmology, and we observe structures in the universe. So maybe that could be a way, and this has been used to constrain some alternative formulations of quantum mechanics, which are also tested in the lab, but for which you can show that cosmology gives very competitive or very complementary constraints on modifications of standard quantum physics. So today I will use the standard quantum theory. Okay, I will not go in those alternative theories, but just to mention that they can be discussed as well. I also mentioned, for those of you who are experts in cosmology, that here I will consider inflation. It's one of the leading paradigms to describe the early universe. There are alternatives to inflation, okay? But in fact, all of those alternatives, except from one, use the same mechanism of amplifying quantum fluctuations. They just use a different background, a different expansion history for the universe, but the mechanism is the same. So what I will discuss today will equally apply to those scenarios, although for explicitness, I will use inflation to be explicit. So most of the time, we don't really see this question discussed by cosmologists. And the reason is that, in fact, we measure, so if we use quantum mechanics to describe the early universe, then we predict things which are in perfect agreement with the data. And this is often taken as some indirect confirmation, okay? The theory gives us something that we can observe, but in fact, there is no direct proof that we can use quantum fluctuations in the early universe. And so what we would like to find is some direct evidence, okay? So there is some tradition of working on this topic, which goes back to at least the early, the mid-90s or something like that. So here I've just mentioned a few names of people working on that. I will not go through everything that has been done. I will just choose a few selected topics. But there is, of course, a lot of, there has been quite some activity around this, so don't take it as a complete review on the topic, but just a few interesting ideas. So one key concept that I will make use of is the fact that, well, essentially the quantum and the classical words, they are different because they allow for different types of correlations. Okay, so what is different between quantum and classical is that in quantum theory we can correlate things in a way that would not be possible in classical setups. A typical example is quantum entanglement or Bell inequalities, which are even more famous now that they are in the Nobel Prize, not the recent Nobel Prize, but the one of the year before, given for the experimental detection of Bell inequalities. If you create entangled pairs of particles, so entangled spin, and if you measure the spins of those two particles at two different locations, you can find that there are sometimes, they can feature a correlation that you cannot explain in a classical setup. So very schematically, the idea is, the question I want to ask is, can I do something like the Bell inequalities, but for cosmological fluctuations? Is there an experiment or is there an observation I could perform that would tell me whether those fluctuations in the early universe, they come from quantum mechanical process, or maybe they are just classical thermal fluctuations, for instance? So schematically, I take my cosmic microwave background, I measure the temperature at different locations, I want to construct some correlator that would reveal the presence of quantumness. So I will do this in different steps. And the first one is I will try to answer this question at the very theoretical level. So I will not try to construct such an observable explicitly, but I will ask a more naive question, which is there something quantum in principle? Okay, so I'm not trying to see in practice how I would measure it. I'm just asking, is there something quantum in principle in the correlations of primordial fluctuations? And there are different tools in quantum information theory that allow you to answer this question. One of the most recent developments is about quantum discord. I will explain what it is. It's a tool which is supposed to characterize the presence of quantum correlations. So the idea is the following. Imagine that you have two systems, which I call A and B. And A and B can be in different configurations. A can be in configurations AI, B can be in configurations BJ. And I want to see how those two systems are correlated. So at the classical level, so if I want to describe those two systems classically, what I can do is I can introduce some probabilities, P. So P of AI BJ is a probability for A to be in the configuration AI, for B to be in the configuration BJ. Then I can marginalize. For instance, I can compute the probability to be for A to be in AI by just summing over all the possible states of B. And then there is this von Neumann entropy, which describes the amount of uncertainty in the state of A, for instance, which is defined in this way, minus the sum of P log P. So for instance, if you can show that if the entropy vanishes, that it means that one of the A here is 1 and all the other A's are 0, it means that you know the state of A with absolute certainty. But if there is something you're not sure about A, so if several of the P are not 0, then you find a positive entropy. Okay, so the more positive the entropy is, the more uncertain the state of A is. And then you can show that this theorem holds, which is called the Bayes theorem, which is essentially telling you that the entropy of the whole setup, so the uncertainty in the state of the whole setup, is the entropy in B plus the entropy of A once you have measured B. Okay, so now let's try to find analogs of these concepts in the quantum world. So in the quantum world, I cannot define the state of a system with probabilities, but I have to define it with a wave function, or more generally with the density matrix. At the quantum level, I have density matrices. I can also trace over the state of B. In this case, the tracing over is through a trace. This is why I call it a trace over. So the reduced density matrix for the subsystem A is the full density matrix where I trace over the degrees of freedom contained in B. I can define the analog of the von Neumann entropy, which is just minus trace of rho log rho, where rho is a density matrix. You can also show from this expression that if the entropy of a state is 0, then it means that, in fact, A is in a pure state. So the entropy, the density matrix here can be written as psi psi, a pure state, which is the analog of this statement. So you know what is the state of A with probability 1. It's in the state described by this pure state. However, the Bayes theorem doesn't hold. Okay, so this theorem does not go to the quantum level. And I can explain, I can give you of course, so this is, I mean, there are lots of things to be said about that, but I can just give you a simple example to realize why it's not the case. So let me take a very simple setup where I have two spin particles, A and B, and I consider this quantum state, which is an entangled state, okay? So it's a quantum superposition of having the two spin particles pointing upwards plus the two particles pointing downwards. And then then let me try to see if Bayes theorem is satisfied. So the entropy of the full setup A and B is 0 because this is a pure state. Now I can compute the reduced density matrix of B, for instance, by tracing over A. So I do psi psi, I trace over A. And then what you can show is that you have a diagonal density matrix with 1/2 on the diagonal. So you can easily compute trace of rho B log rho B. And then you find log of 2. And so this means that this equality does not hold because S of AB is 0, as we have shown here. S of B is log 2, as we have shown here. And the entropy can only be a positive number. So of course, 0 cannot be equal to log 2 plus a positive number. So Bayes theorem is violated. And the idea is that because Bayes theorem is satisfied at the classical level, I can use a violation of the Bayes theorem as a measure or as a detector of quantum correlations. Okay, so I take this Bell inequality, so this should be 0 for classical setups, and I call it my quantum discord. So here you find in this expression there is a minimization over pj, so so what is pi j? It's just related to the fact that in quantum setups, this quantity, which is the entropy of A knowing B, depends on the set of projectors on which you measure B. Okay, so it's a technical thing that will not play a role in what I will discuss later. But in principle, if you change the set of projectors on which you measure B, you can change this. So we take the minimum value of that guy. You can show that this is always positive. So if this is not 0, it means that for whichever way you have to measure B, you will always violate Bayes' theorem, and therefore you will have some quantum correlations. So my first task will be to compute quantum discord for cosmological fluctuations. So I need to say a little bit more about the state of this quantum field V. So here again, I recall that I split my metric on a classical quantity plus a small fluctuation. So this guy does not depend on space. It's a homogeneous expanding background. And I do the same for the inflaton field. And then I find this combination of delta phi and delta g mu nu, which I call V. And by doing perturbation theory, you can work out what is the Hamiltonian of this V field. So V, I can expand it onto creation and annihilation operators, which are called C and C dagger. Usually in quantum mechanics, they are called A and A dagger, but in cosmology, A is a scale factor, so we use a different notation. So C and C dagger are the annihilation and creation operators. And I find this expression. So K is the Fourier mode, A is the scale factor, which I already introduced. And epsilon 1, I think I have an expression that should, yeah, it's at the very end. It's just related to the time derivative of the Hubble parameter. So it's another quantity which describes the rate at which the background is expanding. Okay, so let me just clear it up a bit. So what you find, so the structure of this Hamiltonian is fairly simple. You have a sum over K, which means that each Fourier mode evolves independently, but that's because I work at linear order and perturbation theory. And for each mode K, this is the Hamiltonian of a harmonic oscillator. Right? You have a free term here. So you see this term does not create or destroy any particle. You create a particle with K, you destroy it immediately afterwards. The same with minus K. And then you have this interaction term, which is more interesting, which either creates a particle with K and with minus K, or destroy a particle with K and with minus K. So the fact that it has this structure just comes from the fact that your theory is invariant under rotation. So if you create a particle with K, you should create a particle with minus K to preserve the momentum conservation. And it is so it is an interaction term between quantum fluctuations and the classical background. It is controlled by this quantity, which depends on time. You see there is a time derivative. So if you're on a flat background, if there is no dynamics of the expansion, this guy here is 0 and you just have the free term. Because the universe is expanding, we have this new term here. Which acts as a pump field. Okay, so it's a time-dependent coupling constant. It means that, in fact, this is not a harmonic oscillator. It's technically a parametric oscillator because the frequency of the oscillator depends on time. And this will lead to particle creation, what I was mentioning before. So from this, if you know the Hamiltonian of the theory, you can solve Schrödinger equation. And if you solve Schrödinger equation starting from the vacuum, what you find is the following. You find that the quantum state of each Fourier mode is given by this expression. So this expression represents what we call a two-mode squeezed state. So two-mode is because there are K and minus K, and squeezed, I will explain in a minute why we say it's squeezed. So you see it's constructed out of a sum of states which contain n particles in K, n particles in minus K, again because of statistical isotropy. And the sum is controlled by two parameters, Rk and phi k, which we call the squeezing amplitude and the squeezing angle. So it's only given by those two parameters. And essentially, the Schrödinger equation tells you how Rk and phi k vary as a function of time. Okay, so you can work out equations of motion for Rk and phi k. The details do not matter. Let me just show you the plot, so the solution of those differential equations. So this is how Rk varies as a function of time. So in the infinite past, R is very small, it's close to 0. You see that if I replace R by 0 here, I kill all of those terms. The only term that I keep is the one for which n equals 0, so which means I start from the state with 0 particle in K, 0 particle in minus K, which is the vacuum state, okay, so it makes sense. And then whenever A crosses A star, so what does it correspond? A crosses A star, it corresponds to the time when the Fourier mode K crosses out the Hubble radius. Okay, so on the left-hand side of the panel, I'm inside the Hubble radius, so there is no part, nothing happens. I stay in the vacuum. But then whenever I cross the Hubble radius, then something starts to happen. And this something is that R starts to increase. In fact, you can show that in this state, R is related to the number of particles through this relationship. So when R increases, I start to create particles. And you see there is a hyperbolic sine function, so it's exponentially dependent on R. So when R grows, the number of particles will grow exponentially. Fi is also something doing, also has a dynamics which depends on whether I'm inside the Hubble radius or outside the Hubble radius. So those states are very strongly squeezed. So we usually measure the amount of squeezedness of a state through the value of R. And the scale, for the scales that we observe on the cosmic microwave background, at the end of inflation, R is of order 50. While people trying to build squeeze states in the lab, people doing quantum optics in particular, they're very good at this. They can manage amounts of squeezing which are of the order of R, maybe 4 or 5, something like that. And it's a logarithmic scale. Okay, so 50 is really, really, really much more than 4 or 5. So it's, I believe it's the strongest squeezed state that you can find in nature. So it's quite an extreme quantum state. It is, of course, an entangled state. You see, it's similar to the combination of spins that I was discussing before, except that instead of having 2 possible spins up or spin down, it's constructed out of an infinite tower of states, but it's still an entangled state. And so maybe, so you might think that because it's an entangled state, it would have some non-vanishing quantum discord and maybe some quantum correlations. And this is indeed what happens. So, well, this is again R as a function of time during inflation. Those states, for those states, you can compute quantum discord. So of course, I skipped all the details. I just give you the final result. What we found in this 2015 paper is that discord only depends on the squeezing amplitude. It does not depend on the squeezing angle. It is given by this function. Okay. So if you plot it, it's something which roughly grows linearly with the squeezing amplitude. So if R is of order 50 at the end of inflation, it means quantum discord is of order 150, which is again by far the most discordant state that nature has ever produced. Yes?
Something that just came out to be the strongest correlated one, or is an example of what is possible?
Yeah, so here I consider a typical, a K that would correspond to the scales that I observe in the cosmic microwave background. So you're right, so the result strongly depends on K. So for scales which are much larger than that, discord is even bigger, but for scales which are larger than that, I do not observe them because they are outside my observable. And then for scales which are much smaller, they also have a much smaller quantum discord.
The question is whether the K minus K interaction arose natural.
The K minus K?
The K minus K interaction in your Hamiltonian arose naturally or you put in by hand?
What is K interaction? Sorry.
The interaction between the K and minus K.
No. So this is just a, sorry. I misunderstood the question. No, so this is just, I just wrote the Einstein action. Okay, so gravity described by GR. And then I just expanded in the amplitude of the fluctuation. And then I just get this. So it's just a consequence of, yeah. I've not assumed anything. Of course, sorry, so I should say, I made one assumption. So this interaction depends on the way that the scale factor depends on time, right? Because it was A prime divided by A, there was this epsilon1 parameter and so on. So of course you have to assume something about the way at which the universe expands during inflation. And here I took some standard evolution which is compatible with what we observe, which is that A grows almost exponentially with time. We call it a de Sitter universe, but all measurements we have, they are compatible with de Sitter or quasi-de Sitter expansion, so yeah. So that seems to suggest that we live in a highly non-classical state, and that maybe we can violate some Bell inequalities with it. So now I will try to move on and find explicit Bell inequalities that I could violate with them. Yes. Yeah. So I will come to decoherence without decoherence. So the idea of Bell inequalities, I just recall the sketch that I was displaying before, is if there is a source of entangled spin particles here, which shoots a particle here and shoots a particle there, and then Alice and Bob measure the spin of the particles they receive in different directions. Yes, sorry. Yes.
Inside the Hubble radius.
That's
right?
correct.
But
Yes.
still we know that those are quantum states. But here you are getting quantum discord is 0 for that particular.
Yeah, because they are in the vacuum state.
Yeah, but those are still quantum, right? So when
Yes,
we
yes.
say that the discord is 0 for classical state,
Yes.
right? But here the discord is 0 for a quantum state.
Okay,
Right?
so sorry. So the statement is not that discord is 0 for quantum for classical state. It's just that if a state, so everything is, I mean, at the end of the day, everything is quantum, right? If you use, so any state should be a quantum state. But if a quantum state has a vanishing discord, then it does not contain correlations that you could not explain with the classical state. Okay, so it's just a way to see whether there are correlations in that quantum state that I cannot explain with a classical setup or not. So vanishing discord just means that. Just means I can also find a classical state that would share exactly the same correlation structure, and so you could not tell the difference. Exactly, exactly. So I use it in the opposite way, which is if I have a non-vanishing discord, then I can be sure it's not classical. Yeah. I think there was a, yeah.
Considering here Schwinger pair production in the gravitational field,
Yes.
and then the idea is that if you have a pair production, then they are quantum pairs because it's a correlated pair. So they will anyway give rise to quantum fluctuations.
Yes, that's right.
Okay.
Yeah, yeah.
And this pair production naturally happens in gravitation, or you have to put in a strength to produce pairs? Like you have a minimum strength of gravitational field to produce pairs. Like for example, Schwinger mechanism, we have electric fields which are of certain strength, which can produce them.
Yes, yes, this is a good point. So, so no, there is no minimum. There is no minimum scale. If you have a, so I mean, of course, we know that inflation took place at a scale which is higher than a certain lower bound, but we know this not because of that. We know this from some other cosmological considerations. It has to be early enough in the universe and so on. But theoretically, if I take the energy scale of inflation down, this mechanism still occurs. Of course, at a rate that will depend on the energy. So the higher the energy, the even more efficient the production is. But it's a continuous thing. There is no threshold. Yeah. So here in this Bell setup, so Alice and Bob measure the spins in different directions, and then you can construct this Bell operator, which so Alice measures the spin in the UA direction. UA is a unit vector. Bob's measure the spin in the UB direction. You take the product of the results, and then you do it for another set of directions, a third one, a fourth one, and you construct this linear combination. And you can show that if there, this is Bell theorem, that if there are only classical correlations between those two spins, the expectation value of this B should be less than 2. So whenever you measure experimentally B larger than 2, then you have found violation of classical probabilities, which is a signature of quantum physics. Okay, so the Nobel Prize of a year ago was given to people who actually detected violation of this inequality. So what do we need to violate Bell inequalities? We need a bipartite system, the equivalent of the two spins, but for cosmological fluctuations, we have this K minus K decomposition. We need an entangled system, which here we also have because we have a two-mode squeeze state, which is an entangled system. And then something which is a bit less known is that we need improper operators. So we need spin-like operators which resemble the spins of those two particles, but they need to be improper. So, and this I will explain in a second what it means improper and why it matters. So to explain why it matters, let me just introduce a tool which is common in quantum analysis, which is the Wigner function, which is just some sort of Fourier transform of the wave function. So you see, you from the wave function, you can construct the expression. The details here do not really matter, but what you construct here is a function of phase space. So V is you can see V as the position variable, P is a conjugated momentum. So out of the quantum state, you can construct this phase space function. And you can show that for the two-mode squeeze state, this phase space function is a Gaussian. So this is why two-mode squeeze states are said to be Gaussian states. And if I look at the contour of this Gaussian function, I find that it is typically an ellipse, which for R, when R is large, is very squeezed. Okay, so this is why we call it a squeezed state. It's because the ellipses in phase space are very much squeezed. But the point is that it's a Gaussian function. So in particular, it's a positive function, which will play a role in what I will say afterwards. So one thing you can do with Wigner function is to try to see how they evolve in time. The Wigner function is constructed out of the wave function. The wave function evolves with the Schrödinger equation, so you can work out how the Wigner function evolves. And then what you find is that the Wigner function evolves by taking the Poisson bracket between the Wigner function and the Hamiltonian. This equation is well known. It's called Uville equation because it also describes the dynamics of classical processes. Okay, so what it means is the following. Here is the Wigner function at initial time. So it's a non-squeezed Wigner function, not yet. But because it's a positive function, I can just see this, just for the sake of the argument, as a distribution function. And I can draw points in phase space according to that distribution function. Now I can let the dynamics evolve. And so what happened here on this slide is that on the left-hand side, I've just used this equation for the Wigner function to evolve it. So you see it has become a squeezed function. And on the right-hand side, for each point that I have drawn, I have used the classical equations of motion, so Hamilton's equation, to evolve the location of the dot in phase space. And you see that the cloud of points here follows exactly this distribution function. So this is what this equation is telling you. So essentially, the Wigner function evolves as if it was representing the distribution function of a set of classical processes. So the dynamics of the Wigner function is classical in that sense, okay? There are statements in the literature which tell you that this only happens at late time during inflation and so on. I'm just saying this for the experts because there was some controversy about that. But it's not true, it happens all the time. It's just a property of Gaussian states, essentially. And the fact that the Hamiltonian here is quadratic. Okay, if you include higher order terms in the Hamiltonian, this is not true anymore, but at this level, otherwise it's always true. Okay, so just a recap of this equation. The Wigner function evolves in a classical way somehow. And the reason why it is useful is that you can use the Wigner function to compute expectation values of operators. So how would you do that? If you take a certain operator A hat, you can also, out of this operator, you can construct also a function of the phase space, which I will call A tilde, function of position and momentum. So this is called the Weyl transform, this transformation between an operator and a phase space function. So with this definition, for instance, the Wigner function is nothing but the Weyl transform of the density matrix with some 2 pi normalization factor. And then you can show that the expectation value of A is nothing but the integral over phase space of this A tilde times the Wigner function. But now you may be concerned that there is a function which is called W, which I can interpret as a distribution function because it's, for 2 reasons, it's positive. It evolves under classical equations of motion, and then I can use it directly to compute the expectation value of any quantum operator. And in fact, because of that, John Bell himself, in a paper which is not very well known, but which dates back from 1986, which is called EPR correlations and EPW distributions. PW here means positive Wigner function. And in this, the conclusion of this paper is that Bell inequality violation requires non-positive Wigner function. So if you have a Wigner function which is positive, everything about the state is classical and there is nothing you can do to violate Bell inequalities. So this is in contradiction with what I just said before, which is that I have found an example of a state which is Gaussian, positive Wigner function, but with a large quantum discord. And in fact, so there is a way out of Bell theorem, which was found in 2006 in another paper, which is also very, very little known. I think it has maybe, I don't know, 2 or 3 citations by Revzen, maybe tens of citations, which in fact shows that this is not true if you have an improper operator. And an improper operator is an operator which is mathematic, which is a bit strange. So it's an operator for which, when you compute the Weyl transform The Weil transform can take values which lie outside of the spectrum of the operators, outside of the set of the eigenvalues of the operator. So most operators that you know in quantum physics, position, momentum, energy, they are proper operators. So if you compute the eigenvalues and you compute the Weil transform can only take values inside the spectrum of the operator. But there are examples of improper operators. And what this tells me is that if I want to violate Bell inequalities, I need to use improper operators. So there is a way to do this that I will, how much time do I have left? Like, not so much, no? Okay, so I will speed up a bit. So there is a way to do this. So the idea is that, of course, on the cosmic microwave background, we don't measure a spin variable, we measure a continuous variable, which is a temperature. But from the temperature, if I represent the value of my position variable on this axis, I can split the axis inside interval, and then I can decide that if I measure the temperature here, I give +1. If I measure it here, I give -1, +1, -1. So in this way, I transform a continuous variable into a spin variable, which mathematically I can write down in this way. So it's a spin in the sense that if I square it, I find 1, because if I square + or -1, I find always 1. And then one can find that it can be complemented by Sx and Sy, which are defined in analogous ways, but in such a way that those three operators, they obey the spin algebra. Okay, so they are like, we call them pseudo-spin operators because they act exactly as spin operators, they have the same algebra. And then one can show that if you compute the Weil transform of those guys, one is proper because it only takes values +1 or -1, but the other ones here can take any value between, any value between -2 and 2 or -1 and 1, so they are improper. Okay, so this is why I'm going to be able to violate Bell inequalities. So this is the result of what I obtain when I compute the Bell operator. Here is the expectation value of the Bell operator as a function of L. L here is the size of the interval, okay? So you can choose the size of the interval to be whatever you want. And you see that, so different curves are for different values of squeezing amplitude and squeezing angle. There are situations in which you never violate Bell inequalities. For instance, this brown curve here, you never go above the 2 threshold. But there is this case, for instance, r equals 3 and phi equals 0, for which you do violate Bell inequalities a lot. So what I've done on the right-hand side is for each value of r and phi, I consider this such a curve, and then I've looked for the value of L at which the violation is maximal, and I've just plotted the value of the maximum amount of Bell inequality violation. And you see that, so this region is divided into two places. There is this dark blue region where you do not violate Bell inequalities, and then there is this region here, the dark red region, where you violate them, and in fact you maximally violate them. So you can show that B can never be larger than 2 square root of 2. It's called the Cherelson bound, and 2 square root of 2 is this dark red region here. So now, of course, the question is, so there are many questions, but one of the questions is, where am I on this plot during inflation? So during inflation, if you remember, R was growing, but phi was decreasing. Okay, so of course, so then it depends how fast those two processes are occurring. If phi is decreasing faster than R is growing, you might just end up in the dark red region. But if phi is decreasing very slowly and slower than R is increasing, then you remain in this dark blue region and you don't violate Bell's inequalities. So as it happens, whether you end up above or below this dashed white line, which is the boundary of this domain, depends on the details of the inflationary potential, on the inflationary model that you consider. Okay, so there are different ways of implementing inflation. And so I'm not going into the details, but some models will give you a violation, some models will give you no violation. This is, of course, one example of Bell inequality. You can, in principle, construct an infinite number of Bell inequalities, okay? So it does not tell you that maybe you can find a better Bell construction that will give you even more violation. But at least with this example, this is what we find. So because my time is almost done, I just wanted to mention one last quick thing, which is that here I've discussed something simple, but which is a little bit on which you could complain, which is the fact that Bell inequalities have to do with measuring things at two different locations in space. And what violation of Bell inequality exclude is a theory which is local with hidden variables, okay? So classical correlations, but a local theory. But here, this is not what I've done. Here, I've looked at correlations between k and minus k. And k and minus k are sectors of the Fourier space. They have nothing to do with local regions in real space. Okay, so you could say, well, we don't measure correlations in Fourier space, we measure in real space, so you should do your analysis in real space. And you can. It's slightly more complicated. This is why I started with the Fourier space discussion. So the idea is that now Alice and Bob should be sitting at two different places in the universe. They should measure this cosmic microwave background at those two different places and correlating the results. So when you do that, let me just keep to the result. But essentially, when you start to measure fields at two different locations in space, so what happens is the following. You still have a Gaussian state, because of course it does not matter if you measure in real space or Fourier space. But the thing is, because the state is correlated in real space, which means that the value of the field here and the value of the field there are correlated. If you ask a question about the value of the field in this region versus the value of the field in that region, what you do effectively is that you trace over the configuration of the field anywhere outside those two regions. Okay, so the field here at x1 and x2 is also correlated with the field everywhere on the screen, but because I ask a question about Alice and Bob only, and there is no third party, in effect, I trace over the configuration of the field outside. But when in quantum mechanics, when you trace over degrees of freedom to which your system is correlated, typically you produce a mixed state. Okay, it's called quantum decoherence. And mixed states are known to feature much less quantum correlations. Okay, if you add decoherence to the double slit experiment, for instance, so if your particles in the double slit experiment, they interact with the medium and you trace over the medium, if the interaction is strong enough, then you don't see any interference pattern on the screen anymore. You've killed all the quantum properties. And in fact, this is exactly what happens here. So by just tracing over the configuration of the field everywhere outside, what I obtain essentially is that, so this code is much smaller, but I don't have any violation of Bell inequalities anymore. So we've tried to look for violations of Bell inequality in the space of the parameter. So R is just the size of the region over which I measure the field, and alpha is just the distance between those two regions. And no matter how you vary those parameters, we never found any violation. Okay, so this is a bit discouraging, but let me just mention one last thing, and then I stop, which has to do with also decoherence without decoherence, although I will have to be quick, is the fact that, in fact, there are other things we can do. So what I've discussed here is called spatial Bell inequalities, which have to do with measuring two spins at two different locations at the same time. And then I found that in real space, there is no violation, although in Fourier space, there is violations. And this type of inequalities relies on what is called realism and the locality of the theory. But there are other types of inequalities. I will just mention those two ones at the bottom. What is called the Leggett-Gork inequalities. So for Leggett-Gork inequalities, I take one single spin variable, but I measure it at 3 different times. And I can also construct an inequality. It does not exactly test the same assumptions. So it tests realism and non-invasiveness, which is the ability to perform measurement without disturbing too much the other degrees of freedom. And what we found is that for Leggett-Gork inequalities, we get back some violations. And the reason is that, so to put it in a nutshell, and then I will stop because I know I'm a bit too long, is that if you have, so what happened in the previous case is that in cosmology, you can show at late time, the fluctuations get frozen. Okay, so this, the density fluctuation or the curvature fluctuation of the universe gets frozen. And the time derivative of that guy is related to the conjugated momentum. Okay, so you have like a position variable which gets frozen, and therefore a conjugated momentum which gets very, very small. In fact, it gets exponentially small. So if you want to find something about position and momentum being non-commuting operators, it's very challenging experimentally because you have to measure momentum, and the momentum has become so small. Okay, so this is why it's in fact very challenging. So this is one of the reasons why we considered measuring those at different times. Because here you can measure, you see here I had to measure the spin in different directions, which means I have to measure position, but also momentum. But this type of inequality works if you measure the spin, can work if you measure the spin at only a single direction, which you can choose to be aligned with the position direction. So this would work if I measure only position at time t prime, t double prime. That would not rely on measuring the conjugated momentum. And it works. And finally, there is this other possibility, which is called bipartite temporal Bell inequality, which is even better because it relies on measuring position only. At two different locations, but at 2 different times. And then it tests exactly the same thing as the Bell inequalities, which is realism and locality. And for that, we also found some violations. Okay, so I had one word about quantum decoherence, but let me just skip it. Here is my concluding slide, sorry. So what I've tried to explain today is that cosmological perturbations are placed in squeezed quantum states in the early universe. Those states are very well known for people doing quantum optics in the lab, for instance. And we found that they have a large amount of quantum correlations, which we measured by this quantum discord. And that gives rise to violations of Bell inequalities in Fourier space. However, we found that in real space, because of this effect, we call it effective decoherence mechanism, the fact that if you trace over other regions, you effectively decohere your state, then quantum discord becomes much more suppressed, and we couldn't find any violations of at least the Bell operator I have considered. There might be other Bell operators which are more clever. And finally, those last 3 things. So one is that now if you measure correlations over time instead of only over space, you might be able to violate some sort of Bell inequalities again. And then 2 things that I've not discussed just as prospects. One is that I've only considered Gaussian states, and the reason is I've done perturbation theory at leading order, so I expanded everything, my Hamiltonian at leading order in the perturbation variable. If I include higher order variables, I will have a non-Gaussian state for the cosmological perturbations. And typically, some of the results I've shown are really crucially depend on the Gaussian nature of the state. If you consider non-Gaussian states, things might happen. For instance, there is a theorem which is due to Hudson and which says that the only pure states with a positive Wigner function are Gaussian states, which means that if you have a non-Gaussian state, if you use the theorem backwards, the Wigner function has to be not positive. There have to be regions in phase space where the Wigner function is negative. And if the Wigner function is negative, this is a whole different story, because it tells you that you don't need improper operators necessarily. And in regions of phase space where the Wigner function is negative, there is something highly quantum, because you cannot describe things with a distribution function anymore. And finally, there is also another aspect which I did not discuss, which is decoherence, so true decoherence. The fact that my cosmological field is also supposed to couple with other degrees of freedom, which I don't observe, or which maybe belong to the UV part of the theory or whatever. And by tracing over them, this will also induce some fair amount of decoherence, which may or may not destroy the signal. Okay, so this is also something to consider. So I think I should stop here, and thank you for listening to me.
Thank you, Vincent, for this very nice talk. So now the floor is open for questions.
So at some point you were working with the Bunch-Davies vacuum state.
Right.
So what motivated the choice for the Bunch-Davies state? It's a highly entangled, it's a maximally entangled state, right? If I'm not wrong.
So Bunch-Davies is what you obtain when you, so if you go to the asymptotic past, so let me just pull back this slide. So if you go to the asymptotic past, this guy here goes to 0, which means that you're just left with the free term, which is consistent with what I was saying before, that in the past, the space-time is effectively flat, not expanding. And so you have a Minkowski, you have a theorem on Minkowski, you have a quantum field on Minkowski, and Bunch-Davies vacuum just says that in this limit, I take the vacuum state of Minkowski, so the state with 0 particle. This is the Bunch-Davies vacuum. and then I let it evolve. So the idea is that, okay, you may ask, why do you start with 0 particle? Maybe you could start with 1 particle or 2 particles. But even if you do so, because the universe expands exponentially fast, even if you put some particles initially, it will get diluted, and very quickly you will go back to this Bunch-Davies vacuum. That's the main motivation.
Thank you.
But of course, it's motivated, but you could also argue that you want to go beyond that, and people have tried it to modify the initial state.
Hi. About its decaying mode.
Yes.
So decaying mode or the conjugate momentum, we know that from, if we assume inflation, that decays exponentially.
Right.
That we know. But from observation, do we have any constraint on decaying mode so that it may not be exponentially decaying if we assume bouncing scenarios or other alternative scenarios, right?
Absolutely.
So from observation, do we have any constraint on decaying mode?
Yeah, it's a very good question. So I think there are some, so I would say the main constraint is what we call acoustic oscillation. So the point is that once the decaying mode has decayed, the phase of the fluctuation is fixed. And the reason is that the curvature perturbation is constant. So whenever the mode re-enters the Hubble radius later, it will start to oscillate because now it sees a flat space-time again. And the initial phase of those oscillations is fixed because if curvature perturbation is constant, it must start to oscillate with a vanishing velocity, if you wish. So each Fourier mode, when it comes back to the Hubble radius, so if I fix the modulus of k, then I look at k's with different directions, but the same modulus. So all those Fourier modes, they come back inside the Hubble radius at the same time, and they start to oscillate at the same time, so they are coherent oscillations, which we do observe in, for instance, bionic acoustic oscillations. If the decaying mode had not decayed, then there would be some remnant of this, and that would kill the phase coherence. So there is some constraint coming from that, but it's a mild constraint in the sense that, so I don't know what the exact numbers are, but I mean, maybe it constrains the decaying mode to be less than, I don't know, % or per mil, while the standard scenario of inflation would tell you it's exponential minus 50. So I think we are very, very far from, okay. But now if you have a scenario where the decaying mode has not decayed, for instance, bouncing cosmologies, or if you violate, as you know very well, if you have a phase of ultra-Strobel, for instance, towards the end of inflation, then the role of the growing and decaying mode gets swapped, and the two can be of the same order. Then, okay, so then I don't know. But this is an interesting possibility. In fact, for instance, if you violate Strobel towards the end of inflation, you may have a substantial decaying mode. So this does not happen in the CMB, at least for the models. But this may happen at much smaller scales. I don't know, for instance, primordial black holes or some nonlinear structure at small scale. Maybe they form with a non-negligible decaying mode, and maybe, yeah. Maybe there is something.
But there might be some upper bound for decaying mode, right? So, I mean, if we go above that, then it can disturb the acoustic oscillation. So there might be some upper bound for, right? No?
Yeah, so the existence of acoustic oscillations gives you an upper bound on decaying mode.
Okay.
I agree. I don't know. In fact, it's a good question. I don't think this has been worked out. What is the exact constraint on the amplitude of decaying mode from BAOs? I don't know.
Thank you.
Thank you for an exciting talk, Vincent. My question is related to this, partly related to what Ratul was also asking. We are saying that this discord is 0 at early times.
Yes.
And if discord is 0 at later times, it may be considered classical, but discord is large, and
yes.
Therefore it's quantum.
Yes.
Okay, so that's one part of the question that seems strange. And another thing is that, look, you are starting from an initial quantum state, and you are saying that I end up with a equally quantum or more quantum state.
Right.
That's puzzling.
Okay. So why? I mean, you think evolution can only make things more classical, or?
That's the picture that was driven prior to this calculation of quantum discord, right?
Yes, yes.
I mean, that's what, it's a squeeze state. It's virtually equivalent to all classical correlations, etc.
Yes. Yes, but I think this has been slightly overlooked. So for instance, this decoherence without decoherence,
Argument.
yeah, there is no decoherence. If you don't couple the system to anything else, there is no
There's
decoherence.
no decoherence.
The commutator between the position momentum remains one, or sorry, h bar, IH bar.
Right.
So it is true that expectation value of a commutator between xp becomes much smaller than expectation value of the anti-commutator,
Right.
xp plus p. Okay, but nonetheless, this commutator is still h bar.
It's still H bar.
And the state you create is a state which gets more and more entangled. Okay, so you start from the vacuum in which there is nothing, and then because the reason is that whenever you create a particle with momentum k, you entangle it with the particle's momentum minus k.
Right.
So you create particles in pairs, and those pairs are entangled. So the amount of entanglement increases a lot. So
I understand.
from that perspective, I would argue that the state is more and more quantum. Yeah.
Okay. So I had another question related to the Bell's inequality in Fourier space.
Yes.
There is a domain where typically you expect R to be large for most of the modes.
Yes.
And phi to be 0.
To be small. Yeah.
Right, well, small, yeah.
Yeah.
And in that domain, R was crossing 2, if I recall correct, consistently. I'm sorry, not R, the expectation value of B.
Yes, but there is a funny thing. So where is this plot? Here.
Yeah. So small r.
Yeah, so small r.
Sorry, large r and small phi.
Yes, large. This is violation of Bell's inequalities. Yes.
Right.
Yeah, but you can. So in fact, you can show. So during inflation, r increases, phi decreases.
Right.
So and every model of inflation will correspond to a certain curve on this. Okay, so I start with r equals 0, phi equals pi over 4. So I always start from here.
Right.
This is like the Bunch-Davies
But I
vacuum.
would have thought that, I'm sorry to interrupt, but I would have thought that all cosmological large scales would end up in that domain, whatever happens towards the end of inflation.
No, so what happens is that when you solve the equations of motion for r and phi, so if you assume de Sitter evolution, so scale factor is an exponential function of time, then you find that for some reason that I don't understand, it's a coincidence, that phi and r are related exactly in that
This
way
fashion.
here.
Okay.
So you go along this white line, which is just at the boundary of the violation condition.
Okay.
Now we know that inflation did not proceed in de Sitter spacetime exactly because we observed some deviations, small deviations from de Sitter in the cosmic microwave background. So if you include deviations from de Sitter, Sorel corrections, then you may end up above or below the white line, depending on, so mostly it depends on the spectral index, okay? So if it's larger than 1, smaller than 1. Now it happens that luckily, if you say that spectral index is 0.96, which is what we measure on the cosmic microwave background, and the running is consistent with that, blah, 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 then you end up below the white line. Yeah, slightly below, not so much below. Yeah. It depends over time, because at the end of inflation, R is of order 50, so you are like
Exactly,
yeah.
right, okay. Okay, I
So
understand.
there is like a, you know.
Okay, I understand, thank you.
So chaotic inflation is rolled out. But it would, if it were not, it would be underneath the white line. It would lead to violations. Chaotic inflation is rolled out because it produces too much gravitational waves, which I've not described here. Yeah. But otherwise, it would be in the violating region.
Any other questions? No. Yeah.
In ultra-slow roll inflation, what we understand is R can decrease for some region during the USR.
Indeed.
Right? Yeah. So then how this plot is going to...
Excellent question. I have no idea. I don't know. I think, no, I don't know.
Okay, so if there are no other questions, all right, let's thank Vincent again.
Thank you.
We have tea and some refreshments outside, so we can join there.